Welcome everybody back to the part 4 of lecture 6, slide number 22. Okay, slide number 22. Look at the due optimal feasible solution right now. Again, trying to mention this is a Primal problem, minimization problem, as minimizes C transpose times X and AX minus U greater than equal to B, AX greater than equals to B. Then I'm adding a negative U as the surplus variable, make it inequality. Both X and U are non-negative. Okay. And for this primal constraint, we have a corresponding omega. Since it's greater than equals to constraint, we have the due variable omega is also non-negative. So here what we're trying to do, suppose the tableau give a basic solution, not necessarily feasible, to the primal problem. So that means right hand side we have some negative value. Okay, and then but all the zj minus cj rows, all the entries, elements in the zj minus cj rows are less than or equal to 0. Then the omega also equals to cb transpose times b inverse. So therefore, it is a feasible solution for the D. Remember last slide we see that, if I go back to the last slide, in the final optimal tableau, and we show you these two are the negative due solution, negative due solution, negative omega. And if I multiply negative, so all the omega will be positive. Also, from the original variables, x1, 0, 0, x1, x2, and x3, we know that x1, x2, x3 are primal variable, but they're corresponding to their due constraint. So we know that for the first due constraint is 0, means what? The first due constraint is tight, which means A transpose times omega equals to C. Second constraint, same thing. A transpose times omega equals to C as well. The third one is not, but it is a negative value. That means A transpose times omega is less than equal to C, which is also due feasible, satisfy all the due constraint. So if you look at here, in the beginning of the due simplex method, they are due feasibility. First original 3 constraint respect to the first original x variable. In the surplus variables portion actually represents the due constraint, the due solution. So what I have, this part is due constraint. And this part is negative due variable. Okay, negative due variable. So this is what I have. Let's look at this part. So we know that from zj minus cj less than equal to 0 and omega is equal to cb transpose times b inverse, also is non-negative. Okay, so it is a feasible solution for the due problem. It also, look at the primal, xb equals to b inverse times right hand side b is greater than 0. Then the omega and x are the optimal feasible solution for due and primal problem respectively. So once we reach the primal feasibility and the due feasibility at the same time, doesn't matter in the primal simplex method or the due simplex method, once these two are both feasible to their corresponding problem, then we have the optimal solution. That's the lemma. That's all about. Let's discuss how this happened. For j equals to 1 to n, which corresponding to the original variable xj, like a previous tableau is corresponding to x1, x2, and x3. And we have is corresponding zj minus cj equals to cb transpose times b inverse times aj minus cj. It's also equals to omega transpose times aj minus cj. It's also equals to aj transpose times omega minus cj. And this is exactly the due constraint. And the due constraint has to be less than or equal to 0. So that's a due feasibility. Okay? So that means this is the due constraint altogether. Look at the next set. For I from 1 to m, these corresponding to the surplus variable ui's in the primal, and we have the following zj minus cj. The zm plus I minus cm plus I equal to cb transpose times E inverse. Since they are surplus variable, so they basically, their aj is actually negative ei, negative unit vector. So they have a negative one on one of the row, and rest of the rows are 0. Okay? And CB transpose times B inverse, we know that equals to omega, so equals to omega transpose times negative ei, and minus 0. So therefore equals to negative omega I. So you understand from the previous tableau, we know that the row 0 on that simplex tableau equals to the negative of the due solution. Take a look. If this is less than 0, negative omega I less than or equal to 0, of course the omega I is greater than 0. And omega I is greater than 0 plus this A transpose omega less than or equal to C, both of them added together, we have a due feasibility. And also, CB transpose times XB currently is my objective function value equal to CB transpose times B inverse times B. And the first part equals to omega and equals to omega transpose times B. And that means primal objective function value equals to the due objective function value. Once they being equal, this is the optimal solution. Okay, so that implies both x and omega are the optimal feasible solution for primal problem and for due problem respectively. Look at this problem one more time. Okay, minimize the C transpose times x subject to A times x minus u equals to b. Both x and u are non-negative. Its corresponding due problem, maximization problem, all right, is B transpose times omega, and subject to A transpose times omega plus V. What is V? V right here is the due slack variable, okay, due slack variable, and I also make it an equality constraint. Since this is the less than equals to the constraint, so I'm adding a slack variable V right here to make an equality constraint. Both U, omega and V are non-negative. We can also divide the primal problem into minimization of a CB transpose times XB plus CN transpose times XN. Subject to A matrix separate, A and U matrix is separate into basic matrix times basic variable, non-basic matrix times non-basic variable, still equals to B. However, what happened? This part equals to 0 because xn equal to 0. So my due problem conclusions becoming, once I separate the B matrix and M matrix, and also the CB and CN, I can actually look at the beta matrix in the due problem right here. It becomes the beta problem. The first couple column right here represents B transpose and N transpose. So I have M columns right here. Also, these are the corresponding what? The identity matrix corresponding to the due slack variable. Okay? So that's all there is to it, and let's take a look. Then, omega and V are the due solution, due variable, due slack. It's a basic solution with omega equals to C transpose times B inverse transpose. But take a look about the due slack. Due slack I can separate into two parts, similar to basic and non-basic. If you look at it, I separate into V1 and V2, and V1 actually equal to 0. Actually, V1 is corresponding to the Cj minus Zj for Xj, if Xj is a basic variable. Remember, in the complementary slackness condition, primal variable times the due slack equal to 0. That's a complementary. Or we can say primal variable times the due constraint equal to 0. Same thing. Okay? If and the due slack times the primal variables also equals to 0. So that means if the due slack for the second part is not equal to 0, then the corresponding primal variable is non-basic. They equals to 0. And they can easily write out by Cn transpose minus Cb transpose times B inverse times N. What is this? Basically Cn minus Zn. Okay? So we can generalize this solution. I just want you to see in the due problem perspective, the beta looks like that. Okay? Because B matrix and M matrix in the primal problem got transposed into the column. Okay? And V1 is, we call that non-basic due slack variable corresponding to the basic variable in primal. V2, of course, is called basic due slack corresponding to the non-basic variable in X. All right, once more, reminder, V equals to C minus A transpose times omega. That's the due slack meaning. If every entry in V2 is positive, in that case we call that non-degeneracy condition, then we have what? Zj minus Cj is strictly less than 0, and for every single non-basic variable Xj. So that's so-called, because V2 is non-zero, then the corresponding Xj has to be 0 and non-basic. Therefore, number 3, complementary slackness condition. Once again, primal variable times due constraint equals to 0. Due variable times primal constraint equals to 0. We're going to show that right away. A transpose times omega plus V equals to C. That's my due constraint. We can separate them out. Okay, separate them out using B and N. Basic matrix is non-basic matrix times omega plus V1 and V2. Equals to the right hand side CB transpose and CN transpose. We stack them together. and that equals to this format we have, okay? B transpose times omega, N transpose times omega, right here. Okay, B transpose, N transpose. And identity matrix with the dimension of M times V1. And rest of the row, identity matrix M minus M dimension times V2. So the first part equals to the cost coefficient for the basic variable. The second part corresponding to the cost coefficient respect to the non-basic variable. Okay, but transpose. Once more, omega transpose equals to CB transpose times inverse. Therefore, V1 equals to CB transpose times B times the CB transpose times inverse transpose. So B and B inverse multiplied together equals to identity matrix. So the result will be CB minus CB equals to 0. So that part is fairly straightforward. So therefore, actually, this part of the matrix equals to 0. So that's the result we are getting. All right, we can write it down as a matrix form. So this is the matrix times omega and V2 equals to CB transpose and CN transpose. And that's exactly, this is the beta matrix right here. A little bit more. I know this part is a little bit long. Once more, omega transpose equal to CB transpose times B inverse, V2 equals to CN transpose minus N times the CB transpose times B inverse transpose. So therefore, this is actually CN minus CB transpose times omega, and that's the exactly the CJ minus ZJ result. So V2 actually equal to CJ minus ZJ, which is a negative of the row 0 we have. So for non-basic column XJ. So the second condition actually immediately already calculated. That's the due feasibility. Okay. So also based on the complementary slackness condition, okay, and X times A transpose times omega minus C equals to X transpose times negative over V, and therefore they has to be equal to 0, and we can prove that. Because this part, if you multiply out XB times negative V1, XB are strictly positive times 0 equals to 0. Xn equal to 0, but negative V2 may not be equal to 0. But something not 0 times 0, and something 0 times something not 0, and of course this result is 0. So this is the straightforward solution. Same thing, we can prove for the due problem. Okay, so since AX equals to B right now, then the omega times AX minus B equals to 0 as well. So this is what we end up with this lecture period. Okay, we finished lecture 6. Here we're giving you some step to formulate a linear programming problem. First is defining variable, including all decision variable. Second is check the linearity, additivity, and proportionality. See if all the variables are, all the objective function terms can be added together, not multiplied together. And also all the x's or your decision variable are proportional to your constraint. Okay. Next is check the continuity. X cannot be integer solution. If it is sum of the x's, decision variable has to take an integer solution or certain constraint, then this becomes an integer programming problem. And we're using slightly different method to approach that. Define the objective function, okay, overall objective function, and then define the constraint, including the non-negativity constraint if necessary. If my variable can be negative, we're using some variable substitution trick, we can reach that, all the variable requirement on non-negative requirement. So this concludes my lecture 6, and we'll see you in next lecture 7, next video.